This is the video of trigonometric basics that we are using to prepare our Algebra 2 classes for the MCAs and the ACTs. And the first thing you see here is that we need to remember the Pythagorean theorem. And the Pythagorean theorem said that in any right triangle, the sum of the two squares of the sides is equal to the square of the hypotenuse. And that's the Pythagorean theorem. So what do you need to know to do the Pythagorean theorem? Well, you need to know that C must be the hypotenuse, no matter what. Now there's two ways to tell the hypotenuse. And the first is something you probably learned back in grade school, which is find the longest side. However, if the triangle is really small, you might not be able to tell which one is the smallest side, and there might not be a label there, quite frankly, because that might be what we're looking for. So what you need to remember is, in any right triangle, the hypotenuse is always opposite the right angle. So as far away from it as you can get, and that's where you're going to find your hypotenuse. So in number 1, it says, what is the value of x? And I notice that x is, in fact, going to be my hypotenuse because it is the side that's opposite that right angle. So I take the two sides, 9, and square it, 40, and square it, and set it equal to x squared. And then I figure out what 9 squared is, and that's 81, and what 40 squared is, and that's 1600. And I add those two together. And now, to get rid of squaring something, I need to take the square root. And I'm hopeful that the square root of 1681 is something nice. So you punch that into your calculator, and it gives you 41. So the hypotenuse in this drawing, the x value, is 41. Then we go to number 2. And I realize this time they're giving me the hypotenuse. So I have to find a side. And it doesn't matter if I put the 48 in for A or in for B. It makes absolutely no difference whatsoever. So I'm going to use x squared plus 48 squared equals 50 squared. The big piece that you have to get is that the hypotenuse must be C in this formula. So this will give us x squared, and then in your calculator you can punch in 48 squared, and you get 2304 equals 2500. And then you go ahead and subtract 2304 from both sides, just using some basic algebra there to undo addition. We subtract, and we'll get 196. And then we'll take the square root of both sides, and that's going to give you 14. And that one we probably should recognize, and that's because most of you had to memorize your perfect squares up to 15 squared at the least. Then number 3. Take a look at it and realize, well, looking for the hypotenuse this time. So, doesn't matter if I do the 16 first or the 30 first. It's 16 squared plus 30 squared, or 30 squared plus 16 squared equals x squared. Now, 16 squared, some of you will remember that one as 256. And then 30 squared is 900. So we'd add those two together and get 1156 equals x squared. And then take the square root and hope that it's something nice that shows up on our calculator, and it is. It's 34. Now, way too many of these are working out way too nice. So I reminded everybody in class that if we get something like the square root of 72, we can't leave that answer as it is. We have to simplify that. So we think we've got a perfect square that'll go into that evenly, and that perfect square is 36. So this will be 6 square roots of 2. That we would get for that. Again, that's not a particular problem on this worksheet. I just wanted you to see one that maybe didn't work out quite so perfect, because they're not all going to in real life. Now, I take a look at number 4 and I realize I have the hypotenuse. So x squared plus 33 squared, or 33 squared plus x squared, equals 65 squared. And those two squares are going to be ones that we have to punch in the calculator because we just don't memorize 33 squared and 65 squared. They're just not something we have a whole lot of use for. So then we'll subtract 1089 from both sides, and x squared will equal 3136, And again, we take the square root, hoping that we'll get a really nice number to pop up, and we do, and that is 56. So the Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse. It is the longest side. It is the angle opposite the right angle as defined in geometry. Do you remember your special triangles? Boy, I hope you do, because that is something that shows up so often in whatever you do mathematically. But if you don't, we had a little song in geometry to help you with that. And it was 30, 60, and 90. It's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3, and it's 45, 45, 90. These are easy to name, for it's 1, 1, square root of 2 in the triangle game. So, we're probably not going to see exactly these numbers when we look at the next examples, but we can remember that by putting an X here, we've basically come up with a formula to find the sides that are not the short side. So this is going to work really nice if we can get the short side. The short side times the square root of 3 gives you the long side, and the short side times 2 gives you the hypotenuse. Now I might have to use those backwards. They might give us the hypotenuse, and we'll have to divide by 2 to get the short side. But we'll wait and see what happens. Same thing with the 45, 45, 90. We can put some X's in here and realize that, again, we want one of these short sides. If they give us a short side, then we can use the relationship between the side lengths of a 45, 45, 90 to get the hypotenuse. So those are going to be isosceles. They will have two sides that are exactly the same, and that's because we have the base angles that are the same. So our base angles theorem tells us that both sides will be the same. So we go to the next page, and in number 5, I see that that's a 30, 60, 90, and I'm kind of wondering which one of those is the short side, because that's the one I hope they gave me. Well, the short side is always going to be opposite the smallest angle. So here's my 30 degrees. Straight across from that, this is the short side. They didn't give me that, so that means I'm going to have to think backwards. So here's my short side. I really need that short side in order to figure out the hypotenuse, but they gave me the long side. So I think back to my 30, 60, 90 triangle, and I remember if this was 1x, then this was x square roots of 3. So I think, what did they multiply by the square root of 3 to get 16 square roots of 3? Well, of course, they multiplied it by 16. And then to go from short side to hypotenuse, so from here to here, you take whatever they have for x and you multiply it by 2. So s is 32. So we actually found all 3 of those sides in that triangle in order to figure out what that hypotenuse was. I take a look at number 6 and I think, okay, 45, 45, 90. Oh, the good news is those are both the same. But they didn't give me the short side, they gave me the hypotenuse. So I think back to my 45, 45, 90, and how if I know what these two side lengths are, all I have to do is multiply it by the square root of 2, and I can get the hypotenuse. But now I have to work backwards. So I'm going to have to take 44, and I'm going to have to divide it by the square root of 2. But we know we shouldn't leave it that way, so we go ahead and rationalize the denominator. We multiply the numerator and the denominator by the square root of 2. And that will give us 44 square roots of 2 over the square root of 4. But the square root of 4 is 2. So we get 44 square roots of 2 over 2. And if you're sitting there thinking right now, can't we reduce that? Absolutely we can. So we would divide the 44 by the 2, because those are both the integer portions of this problem, and get 22 square roots of 2 for p. That's side length. So just using those special triangles there, those special right triangles, makes this go so much faster. In number 7, we have a 45, 45, 90, even though it doesn't look like it. So right away, I think to myself, okay, those are isosceles. This is going to be 9. And then I think, how do you go from the short side to the hypotenuse in a 45, 45, 90? You multiply by the square root of 2. So this is 9. That means y is 9 square roots of 2. And we're done. So that's why it's so great to have the short side. Once you have that short side, everything just rolls from there. So I go to 8, and I see, hey, x is going to be 20. And y? That's not difficult. That's the hypotenuse. It's opposite the right angle. So all I have to do is multiply by the square root of 2. So 20 square roots of 2. Number 9 just happens to be a 30, 60, 90. And I see that they gave me the hypotenuse, but I always start thinking about my short side. So I remember that to go from short side to hypotenuse in a 30, 60, 90, you have to multiply by 2. So to work backwards, we should divide by 2. And 20 divided by 2 is 10. So x is 10. And then to go from short side, because this is my angle opposite that, or side opposite my 30-degree angle, that makes it the short side. To go from short side to long side, I have to multiply by the square root of 3. So y will be 10 square roots of 3. Again, get that short side first, and then do the math from that short side. Number 10 is a 30, 60, 90, but great news, this is the short side. So to get the hypotenuse in a 30, 60, 90, all you do is take the short side times 2, y is 30. And to get the long side in a 30, 60, 90, all you do is take the short side times the square root of 3. So x is 15 square roots of 3. Again, if you get the short side in one of these triangles, you want to just go for it. So now I get to 11. And 11 looks like it's going to be much tougher, but I realize if this is 60 degrees, this is 30 degrees, and this is my short side. And they told me this one is 4 square roots of 3. Well, to go from short side to long side, you multiply by the square root of 3. So to work backwards, you're going to divide by the square root of 3. And boom, you get 4. And then to go from short side to hypotenuse, you multiply by 2. So 4 times 2 is 8. So x will equal 8. And that's why we love those 45, 45, 90s and 30, 60, 90s. Those are supposed to be some problems where your brain can kind of take a break while you're doing the MCAs. And then on the next page we have SOHCAHTOA. So remember that SOHCAHTOA comes from the fact that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So there's our sine, cosine, and tangent. It all has to do with labeling the side lengths of your right triangles. So as we go down to the next example, it says we want all of those trig functions for D. So I'm going to go ahead and circle D. And now what I need to do is just go through and say, okay, the sine of D, that's opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. I'm just going to label all these sides, and then I can find all of those things. So here's D, and 4 is straight across from that. It's as far away as I can get in that triangle, and that's opposite. The 5 is the hypotenuse because it's opposite the right angle, and that, of course, makes the 3 the adjacent side. And adjacent means right next to, but we don't ever want to confuse that with the hypotenuse. So sine is opposite over hypotenuse, which from my labels I can clearly see is 4 over 5. Cosine is adjacent over hypotenuse, which would be 3/5. And tangent is opposite over adjacent. And opposite over adjacent will be 4/3. And there they are. So there's our basic trig functions. Again, we're just using this to set you up to actually use this to find missing lengths or heights. In fact, they like to do a lot of building heights in problems, whether or not it's any kind of testing, MCA, ACT, whatever it may be. So here's our D, and the 8 is opposite, and the 17 is the hypotenuse, and the 15 is the adjacent. So go ahead and find the sine of D, which is opposite over hypotenuse, 8/17. The cosine of D, which is adjacent over hypotenuse, and the tangent of D, which is opposite over adjacent. So get those labels on there, and everything will go pretty quickly. Then, number 14, still looking at D, but now opposite is going to be 5 square roots of 3. Hypotenuse is going to be 10. and adjacent is going to be 5. So opposite is straight across from that angle. So the sine of D equals opposite over hypotenuse, 5 square roots of 3 over 10. But we're not going to walk away from that one because we can reduce both of those, and that'll give us the square root of 3 over 2. Cosine of D equals adjacent over hypotenuse, 5/10, which we certainly had better simplify, to 1/2. And then the tangent of D equals opposite over adjacent, so 5 square roots of 3 over 5, and of course the 5's would cancel out, and we'll get the square root of 3. So what you need to do on the worksheet is use Pythagorean theorem, 30, 60, 90, 45, 45, 90 special triangles, and SOHCAHTOA, so that we can see that you're remembering these pieces from geometry. And a quick reminder that problem number 5 on the worksheet accidentally was exactly the same as problem number 2. So I want you to go ahead and change the hypotenuse in problem number 5 to 2 square roots of 34 to make it a little bit of a different problem as you go through that. That is the lesson for the trig review.